Okay, good evening and welcome to the Thanksgiving Eve presentation for CE3372. There's only two things. This will be a short evening, which I hope everyone's happy about because I guess you have to be here. And in the exercise collection portion, I've added a problem statement for the final project. There's no intent of there being anything new. It's just consolidating everything into one place. And in that is the problem statement. Essentially, you're going to do a hydraulic model of the drinking water system and the drainage system. It has a list of the kind of contents that'll go in the drinking water portion. So this problem statement is written as if these are independent reports, but they can be a single report, just two different parts. And the drainage system contents, and then the sewer system portion is not required for this fall. So you can skip this section. And the elevation data is not required. Use the maps that you have already created in your other exercises relevant to the Somewhere USA subdivision. And I've attached a couple of example reports from past semesters to give you a report structure that you can use to help guide your report in past semesters. So this is from 2015. They were done as two reports. Again, like I said a little bit earlier, it's okay if it's a single report with two parts. And the table of contents gives you a good guideline for the outline of the report. And this particular one is a different location. And so they have an overview map, hydraulics discussion, various screen captures of the different components of their hydraulic modeling exercise, the EPA-NET model, and in their case, how they're handling the supply portion. In the Somewhere USA, you don't necessarily have to have a reservoir and a pump station because the water is supplied from an existing water main. And a couple of example outputs for different pressures, a cost analysis to build the system, and then the various works that were cited. And in their case, they had to do a pump design, which is not part of this semester. They also did a stormwater analysis for the same location. And again, not exactly the same layout of the report, but pretty close. And again, the executive summary, introduction, and how they manage the stormwater drainage for that particular location. And then some assorted layouts of their case in a storm drain, and they're draining to this portion right here, and there's a stream there. What nodes were surcharged, and a profile plot, and finally a cost analysis. I'm actually not sure why the costs are redacted. A table. And then the last part would be for sanitary design, which is not part of this semester, but that's just left there in the problem statement anyway. If you're having trouble sleeping, you could attempt to read this. It should have you out and unconscious in no time, but it shows how to use EPA for sanitary sewer design. So that is the promised or feared last component of the class, and it appears as PR 1-2 or 1/2. And that completes all the graded material for the class. So what I believe there might be some outstanding ES8, ES12, and PR1-2. There'll be a third exam strictly on swim and drainage. From the past, it's been perceived as pretty easy, so it shouldn't be difficult. And that's all the graded material left for this course. And so we're almost done. Now today's lesson is not uploaded yet, but I'll do it locally from the machine on the video. Today's lesson is largely a look at outfall design. No, it's not there. It's in the I think it's old lesson 25. Let's find out. It is. So the last part of all of our water systems, whether it's stormwater or sewer, is we're returning water back into the environment. And that's done through where we locate outfalls. And outfall, nothing special about it. It can simply be a pipe that drains into a nearby stream or river. But there are some design considerations to be aware of relevant to what the outfall can do to the receiving stream that we're trying to send our excess water to. And so the outline for this short discussion is a little bit of overview on stormwater quality management considerations and then erosion control. So we'll first start the story off by talking about sediment. What is sediment? So it's matter that settles to the bottom of a liquid. It can be particles derived from rocks, biological materials, or chemical precipitates. And this thing is disobedient as usual. Stormwater sediments typically are comprised of pavement dust, natural soil, vehicle rust, tire dust, oils, pesticides, fertilizers, dog poop, cat poop, goose poop, and things like that. So mostly the water is water, but it does carry a considerable amount of solids. And these sediments can be transported by the water itself or by wind. And they're created in one in one fashion by soil erosion, and that itself is caused by the impact and dislodgement of individual soil particles from raindrops. So the upper photograph on the right of the presentation is a high-speed photograph of a raindrop hitting exposed soil. And based on the picture, there's a considerable amount of energy transferred to the soil by the raindrop, and then that energy is dissipated by the soil as particles are released. The other way to dislodge soil is to have water flow over soil surfaces, and those surfaces can be just water running over a golf course, or it can be as big as a river running through a town, as depicted in the lower photograph. And in that lower photograph, high flow in this stream at some point before the photograph was taken eroded away this entire embankment, and material fell into the river. These look like structures. A choo-choo train was washed off its tracks. So there's a considerable amount of force in flowing water. And this old jail here, which used to be a few blocks back from the river, is now riverfront property. and all the inmates jumped out the windows and swam away. I don't know if that's true. I'm making that up. So the mechanisms of erosions are depicted in this figure. There's a sheet erosion, which turns into rills, which think of those as little teeny itty bitty channels. And then those become larger and larger and become gullies. And then bigger than gullies would be incised channels that are cut into the surrounding material. And all of that is transported as suspended material. And in the suspended material transport, there's two different categories of that transported material. There's bed material and wash load. Wash load is the solids that are transported completely by the water phase. Those would be particles that, for either density or size reasons, don't actually ever saddle to the bottom. And then bed material is, you can think of the bottom of a channel as a slurry bed. So mostly solids with liquid lubricating everything. And that slurry moves as a bed material. And it'll stop moving depending on what the overlying velocity of the water above it is. So in the suspended transport phase, channels accumulate sediment from the shill, sheet, and rill erosion and the gully erosion. Lighter sediment tends to be carried completely suspended. Heavier materials settle to the bottom and are added to material from the banks. What's depicted in this figure is right down here at the solid-liquid interface. There's a portion called bed load. So these particles, if you will, are still moving along. They're bouncing along and rolling and sliding. And then there's a portion where the bed itself is relatively stable. It's labeled here as a surface bed material, and then there's the substrate. And actually, you'll notice in the diagram, the grading between the surface bed and the substrate is quite a bit different, and that's actually observable in nature. You find that the surface materials are on average larger in particulate size than the substrate beneath them. So you could argue they form kind of an armor to forces that would otherwise attempt to carry the material away. The main governing force is the speed of the water. When the water has relatively high velocity, there's quite a bit of shear force at the bed, and that suspends or resuspends material and starts pushing it downstream. When the velocity drops to a lower level, that shear force is declined considerably, and the bed will remain stable. So in terms of outfall design consideration, keeping that in the back of our mind, velocity is going to play an important role. So the stream bed load is part of the total load that moves along the bottom of the channel. The particles roll, bounce, or slide. And when the stream has the ability to resuspend, any particles that have stopped and have been stabilized can resuspend, and they will continue to move on down slope. When it again loses the ability to carry such particles, they will drop out again, and they will relocate in different parts of the stream. And so in certain ephemeral streams, or streams where the flow is mostly low and there's only occasional high velocity discharges in it, we can observe mounds or waves of solid material that make their way downstream over the course of years, decades. So you have a large pile of rocks at one location in the stream. That same pile of rocks appears downstream 3 years later. So it's sort of a very temporally slow process in comparison to most of our other engineering thinking. It all depends on whatever the localized stream velocity is and the settling velocity of the individual particles. Neither of those two we have a great deal of control of. We have more control of stream velocity than settling velocity. It doesn't make much sense to introduce particles into a flow to somehow protect it. The wash material transport is the material that flows through a reach without significant interaction with the bed. That material is usually coarse sand, quite a bit smaller in size. These two figures are of the same location, a place called Guadalupe Arroyo, between Guadalupe Peak and El Paso on US, I think it's 85, or yeah, it's 85. And there's a bridge there shown here. We're down in the stream bed, not in this condition where there's a pretty large flow coming by. And out here, I want to call your attention to a power pole that's located right there, and what looks like a trailer, but it's actually a Guadalupe Arroyo School. And there's the same pole here, and the trailer's off about there. So the photographs are roughly from the same location. The one with the water in it is taken from on top of the bridge, and the one without the water in it is taken from down in the stream bed. And during these higher flows, you can see that there's a considerable amount of relatively fine material, coarse sand that's been deposited on the backside of this support bend. And so at some point in its near past history, the bed load level was up here, and then as the water receded and washed away, it left behind the residue. And you can see quite a considerable accumulation of solids in this particular portion of the channel. Less so here. Now this is deceptive because you see the wheel tracks. There's been machinery moving up and down here. So this material was probably a little bit higher than it is in the photograph. But knowing the shape of this particular stream at this location, it's not surprising that there's deposition here on the inside of this turn, because this is the outside of the turn where the cursor's moving right now, and that's being eroded away by this water that's being redirected to come under the bridge. Oh, I do have a pen today. I can actually draw. So to human beings, the stream path looks about like that when you're standing from the bridge. If you were to look out there, that's which way it would look like water flows. But to water, the stream path is more like that, and then it's being forced to make a turn, and I'm exaggerating it with the second drawing. And so this portion of the stream bank is being eroded away, and it corresponds to this portion here. So we think the water nicely wants to turn through there, but it doesn't. It actually is taking a much wider turn, eating away at this bank, and if you think of it, the water out at the outer edge of the turn has higher velocity, and so deposition occurs on the inside of the turn. So the pictures are actually quite explainable in general, in generalized terms. And here's another view of the same set of head cuts. The water is roughly flowing this way. Now the picture's deceptive because there's been some machinery work. The stream actually is supposed to be coming from here, but because of the way there's been earthwork in an attempt to protect both abutments of the stream, it's redirected to the point where it actually swings wide, and it's coming like that to make its way through the bridge opening. And if we're to look at a cross section, we'll do that in a different color. Let's do it in yellow. I think that'll show up good. If we were to look at a cross section, the cross section that we perceive is something like that. But the cross section that the water perceives is more like that. And those differences in cross sections are somewhat important for the soil deposition. The amount of solids materials that's transported by water can be quite stunning. Here's a photograph of a bridge abutment that's essentially been washed away by a mere 6-hour rainfall, quite a distance upstream of where the photograph is taken. And this road in this photograph is, for all practical purposes, unserviceable and actually unsafe. There was a portion of the material that fell in moments after the photograph was taken. Fortunately, nobody important was standing underneath it. The other thing that's transported by water are buoyant debris. Here's a few photographs of buoyant debris making their way past engineered infrastructure. And the interesting ones are there used to be a bridge there, and it's gone. Was carried away by buoyant debris. And here you can see a portion that's almost gone. It's a tipping bucket bridge, if you will. And it's about to fall over. On the upside, most of the vertical supports have survived, so replacing these, at least for temporarily use, is not as hard as it could be. I think this photograph, by the way, is Devil's River somewhere. I don't know where this one is. I don't actually know where this one is. In this lower photograph, you can see quite a bit of debris has been deposited on the parapet of the bridge, and there's a debris line here where the high water was. And so it's not too difficult to see that the high water was something like that. It was flowing up over the top of the bridge deck because there's some more debris caught here. But now that the water's receded, everything's going the way it's supposed to, and the maintenance crews have to deal with all these buoyant solids. So the lowermost picture is a maintenance, a cleanup issue. This picture is a problem because the buoyant debris trapped up against the infrastructure, and there was enough water forces combined with that debris to push the infrastructure over. So those are extreme cases of solids. We are most likely not going to produce outfalls that themselves can produce that kind of damage, but they could conceivably contribute to it. So stormwater management itself, as we've discussed earlier, comprises structural and non-structural measures that have three main goals in life: to control how much, so that's a quantity control, when it arrives, and how dirty it is. And as an example, to some extent, we can control all three using a detention pond. We can have some control of quantity by preserving soil and allowing infiltration to occur. Not infiltration of the inflow and infiltration, but infiltration of water into the soil. Arrival time we can control with channels and ponds, and then quality, filtration and ponds is about it. But the other way to control quality is to prevent solids or pollutants from getting in the water in the first place. So some of those management practices are depicted on this slide in these three figures. So there's a photograph of a detention pond, brand new, ready to go into service. A rock filter dam, so the pile of rocks that we see in the roadside medians aren't just the construction company putting leftover rock down on the ground, making it look like they did it on purpose and getting paid for it. It actually has a purpose. And the purpose is, if, say, the flow is from left to right, what otherwise would flow in this ditch, if it's big enough, there'll be some ponding. And in that ponding, solids can deposit. The residuals form on one side of the dam, and they protect the water quality moving on its merry journey down to the receiving water. The other structural method depicted in this third photograph goes by the name of vegetative buffer strip. It's just a lawn that's put between a source of storm water that may be polluted and a receiving body. And so when it rains, the flow would be across that buffer strip to the receiving body. And it's been studied for a number of years that there's actually considerable water quality improvement by having the water coming off of a highway flow across that buffer strip before it gets to the collection body of water. It doesn't seem like it should perform as well as it does, but indeed it does. So that's a good use of right-of-way for a water quality purpose, as well as in case of highway engineering, there's quite a bit of safety benefit from this buffer strip to keep errant vehicles from hitting errant kids on bicycles. Gives the kids on bicycles a chance to get away from the Jeep that's plummeting at them at 60 miles an hour out of control. Many of these practices are contained in various guidance documents. Here's one from the Texas Department of Transportation. So the picture is dated 2002, but it was actually updated 2013. The practices don't have to be devices, although usually that's what they are. And namely, they're all aimed at erosion control. And in erosion control, there are two regulated parameters, which is turbidity and total suspended solids for stormwater management. What we as engineering design can have some impact is we can exercise some impact over overland flow through channelization, detention ponds, rock filter dams, what have you. We can exercise some impact over surface flows, which are pretty much the same thing as overland flows. I'll pick on Texas A&M because they made this graphic and the poor Aggies couldn't tell the difference. That's mean of me. We have a little bit of engineering control over infiltration. Most of the remaining forces in erosion are outside the realm of economically practical engineering. Of course, with global warming, you can argue that we're having an impact on raindrop impact by reducing the amount of rainfall. That'll make the erosion better, but that's a pretty costly thing to do for society. And continuing on in that particular document, it suggests some different practices that lead to erosion control. And probably the one of interest is this second bullet item. Protection at culvert outlets and other stormwater outfalls. That's a big deal because we're adding water back into the system. We don't want to add water in such a way that it has high velocity and that combines with the water that's already there and actually erodes out the stream that we're trying to use as a receiving stream. So our general goal is we want velocity at outfalls to be small. Doesn't mean a discharge has to be small. We just want the velocity to be small. So if we recall back earlier in our open channel stuff, if we had this channel carrying a particular flow, the velocity is simply the flow divided by the area. We can reduce the velocity by making the cross-sectional area bigger. So there's actually a technique called a level spreader that does that. See, make the velocity lower there. I'll make this one longer to represent a bigger velocity. So that's really what our goal is doing, is we want to control the length of that yellow arrow, which is our velocity arrow. And the main tool we have is to deal with a discharge area and or the total energy contained in the water. Because the other thing we probably don't want that to be supercritical. So some of the design guidance are to make the slopes flatter than required by soil considerations. We do have right-of-way issues. Protect bare soil. That's kind of a duh. Delay runoff and reduce peak flows. So one trick is to delay the runoff so that the peak runoff is not as big as it would be in the absence of retardation features. Reduce peak flows. We can do it with various engineered devices. The one that you're working on at homework is the Mighty Pond. In other instances, we have relatively steep slopes that we have to convey water. And in those instances, if we have to convey water over a pretty steep topographic slope, we may not have much choice in velocity management. So instead, we have to manage the material that the channel is made out of. And I'm drawing trapezoids on what is a chute. And so the water is coming down this way. And so these rocks are sized so that at their design velocity, when water comes off this steep chute, that the water does not have enough energy to mobilize those rocks. That would be kind of stupid in a sense, to put all these rocks custom placed by the rock placing experts and then have them all washed to the bottom of the slope. And then you still get the erosion up here on this soil that you're trying to protect. Alternatively, we can have a case where we're transitioning from concrete line, which is quite resistant to erosion, to a natural channel, which is not resistant to erosion. And so the water coming down, we force a hydraulic jump with these energy dissipators. And then the idea is to get this into a pool of relatively low velocity as it makes its way on downstream. The hydraulics of such management is accomplished pretty much by everything already discussed in the course and your other fluid mechanics in your hydrology course. There's nothing particularly secret about the required hydraulics. There is some added effort converted in velocity management for the purpose of controlling erosion and sizing storage facilities. And in the outfall design, we have to pretty much accept that velocities are going to be high. And I'll show you a graphic shortly that will illustrate that. And so we want to use vertical drops when we can to use up the energy. Plunge pool, which is a type of vertical drop, to help use up the energy. And if we can't convincingly use up the energy in the flowing water, then we would have to consider armoring. The main practical problem with armoring is that it doesn't work very long. Generally, if that's our only solution, we've probably made some conceptual mistakes elsewhere in our system. That doesn't mean abandon armoring. It gets used. Here's an example from that 2002 manual on stone structures, and it's where we need to dispose of runoff at a protected outlet or diffuse concentrated flow before release back into the environment. And then there's a typical conceptual design where we have a berm with a low spot, so we want water to come out of this lower spot. We rock armor that berm so that it doesn't itself wash away. And on the downstream side, not depicted in the drawing, is we provide armoring so that the flow that comes out of this berm ponds behind it, slows down, and makes its way over the top and on down to the stream. So that's one way. Another technique is, I kind of like this one because it's actually fairly ingenious. If we have a flow up here, we have a berm protecting it, and we need to convey it down to a substantially lower elevation, we can use a pipe, fairly large diameter, and run it down the side of the berm. Slope doesn't matter. Have a fairly sharp change in slope near the end of the pipe, not at the end of the pipe. And what will occur is we'll create a hydraulic jump. Will occur inside the pipe, and we can select a pipe material that's more than capable of withstanding the forces of that hydraulic jump. It uses a lot of energy, and then again in the receiving stream we provide a little bit of armoring right where the water comes out, and then it makes its way on downstream. So that's another energy dissipator, and there's quite a few more in this document. Here's a photograph of an armored outfall structure, and based on these interlocking pavers, it looks like they provided for flow coming down the side of this berm, comes down onto this apron, combines with any flow that's already down in here, and makes its way on to wherever it's headed. And the armoring is conferred by these interlocking paving stones. The placement of these is not cheap, but it's fairly attractive because they're put in place, backfilled with soil, and vegetation can grow up in the open cells between the interconnections, and that tends to make them fairly rugged and capable of handling the high-speed shear forces that occur during the high flows. So that's one type of armoring, and it goes by a lot of different names: interconnected porous pavers, revetment, interconnected revetment, a lot of different words. Here's a diagram of an unintentional plunge pool, but it illustrates what a plunge pool is supposed to be. So there's the pool that receives the high energy water out of the pipe. The bottom of the pool is probably fairly deep, and then we have the outlet to the pool coming along here, and so we've used up a lot of the energy when the water plunges into that pool, and then we have a fairly wide, comparatively to the water flow, cross section for water to make its way on downstream. Now this happens to be at a beach, and from these missing bolts in the flange, it appears to me there used to be more pipe coming at us, and it was lost at some point in history and never bothered to be replaced. And so here's mom telling the little boy, don't go playing in that nasty water. Here's another type of plunge pool design. To me, this photograph looks like it was intentionally designed, and there's quite likely grouting that's been added into these existing rocks so that the high energy water comes down hits these rocks, which play the role of an energy dissipator, make their way into this larger pool, which in turn connects on downstream. I think it probably goes this way around this object. So the energy that was in this water is dissipated on these relatively stable rocks, and any solids that were conveyed or washed away in the rocks are captured in this pool before it goes on into the larger receiving stream. And then we get the cases where nothing seems to work and we just armor the heck out of everything. So here the flow would be coming out of this pipe, and the engineer put these energy dissipators, a weir. The weir, I suspect, was actually for flow measuring. And let's see if I can see the, I can't see the bubbler pipe to measure flow, but you wouldn't necessarily put a weir there just for show. We have these wing walls, which are made out of concrete, and that should have worked. And it appears that later on, a large pool formed during flows, and we got erosion in this area. And so a later project introduced these large rocks to help keep the soil in place. And from a design standpoint, something needs to be done with this portion where there's been massed wasting. And that arguably may not have anything to do with the outfall other than being located at a place where the outfall contributes to existing stream and creates a gyre or a circulatory effect that slowly washes away this soil. So this is a pretty darn engineered outfall. And it even has guardrails so that when you're watching it wash away the soil, you don't fall into the flow. Other places that are strictly water quality features, here's a photograph of one that's it's off of exit 223 on Interstate 25 in Albuquerque by the airport. The flow comes into this device. The photograph doesn't capture the whole thing. There's a stream that diverts flow into it. It actually comes underneath all the stuff that we're seeing, goes into this grit chamber, which captures all the floatables and large objects. This wall right here that the bird is sitting on, the flow goes down there, up and out here as you see it, over these screens, and then the water goes that way and returns to the stream. So this is strictly a water, apparently strictly a water quality feature. And the goal is to get the solids out of the water. It's kind of cool in the sense, and this works. So all these flow change directions seem exotic because they have really high food numbers in Albuquerque coming off of the Sandia Mountains. There's plenty of energy to do work with. So in addition to providing water quality benefit, it's also using up an awful lot of energy in the stream flow that would otherwise continue to erode the channel. And this particular structure is located at a transition where the channel goes from concrete lined to a natural channel. So it goes from non-erodible to erodible. So that there's a need for something to use up that energy. And here's another photograph of the same type of structure. It's brand new before it ever got any soils in it or graffiti on it. Seeing that much unpainted concrete out there, unpainted without any graffiti, is kind of amazing. Here's yet another photograph of some intentional armoring. In this case, the storm sewer pipe is here, and the engineers specified the stabilization with very large stones built around it. You can tell from this terracing that these are put here on purpose. This is not something nature just happened to do because the pipe was there. So all these large stones were placed there on purpose, and the purpose is clearly when this pipe is flowing relatively high flow, there's going to be pretty substantial velocity, is to protect the underlying substrate, which we can see here on the right of the picture is pretty fine, clearly erodible material. And then when nothing else works, we resort to our friend concrete. This particular photograph is a transition from a engineered or an unnatural channel to a natural section. So about here, probably trapezoid, it'll probably have a pilot channel in it. And then we get to the sort of natural section. And so these energy dissipators are provided so that the flow coming down the engineered channel, when it enters the natural channel, is used up enough of the energy that the velocities aren't so high that it starts to erode away the natural channel. And this vegetation right here is indicative that at least at the time the photograph was taken, the protection appears to be functioning. So all these are based on velocity. The diagram here is called a Holstrom diagram. And on the lower axis is particle size, and they're all assumed to be geologic particles, so their specific gravity is about 2.6. And this vertical axis is mean section velocity. And there's three areas on the diagram. There's a zone of deposition, a transportation zone. Diagram has a weird shape indeed. Over here, and then the erosion zone. And so for any particular natural system, if we're to plot the mean grain diameter and the mean velocity, let's say it plots right in here, the chart is telling us that that material, if it's already in suspension, is likely to stay in suspension and be transported downstream. Likewise, if, let's see, let's change the particle size. We'll stay at the same velocity. If we plot over here, the chart is indicating to us that in that system, the solids are likely to deposit somewhere in our channel, and the water moves on downstream as a clear water. If we stay at the same particle size and increased velocity, it plots up in this region. The chart is conveying to us that in that system, whatever the natural channel is made out of is going to tend to erode away. So the idea that we want to focus on is trying to stay out of that erosion zone after our outfall. In our sewer system, erosion in most senses is usually desirable because it keeps the solids moving downstream to the outfall. But once we get to the outfall, we don't want to erode any more solids. We just want our solids to go back to nature and get deposited and make pretty plants. So here's the same diagram, somewhat modernized, and in this picture, the areas are color-coded. So we have this orangish area for the transportation zone, red for the deposition, blue for the erosion. The color coding is kind of odd. I think erosion is bad, so I would have made that red, but that's beside the point. The idea is we want to stay outside the zone, but if we look at our relatively classic design features in our sewer systems, we tend to make them to operate in the 2 to 10 foot per second range, which pretty much means that everything we're going to work with smaller than a pebble, if our receiving stream is made out of stuff smaller than pebbles, such as clay, sand, clay, silt, and sand combination, if that 2 to 10 feet a second is maintained after the outfall in the receiving stream, we're actually going to start to erode things away. If we get to the lower end of the range, down here, and we're discharging into a mostly sand stream, we'd probably be okay. But at the upper end of the range, we're going to erode everything. If we're depositing at the lower end of the range, mostly into a clay stream or a silt stream, also okay. But if we get to the upper end of the range, we can induce erosion. And so this blocked area here is kind of the danger zone based on what the receiving stream is made out of. And our general idea is to reduce velocity until it can't erode the receiving stream. And what really matters is the velocity at the bed. What we treat as velocity is actually the mean section velocity. And so we have to keep this figure in mind as we're picking our velocity reduction schemes, because it's not normally economically convenient to flow profile receiving streams. It doesn't get done that much. So in terms of our outfall considerations, for a given discharge, we're moving along the specific energy depth curve, and we want to get up into this region, because in this region, the velocity head is pretty small, because that's what's making things erode. But if we're down in the supercritical region, velocity head can be quite substantial. So we want to reduce velocity, and based on this diagram, one of the ways to reduce that is to increase the water depth at the outfall. That's the idea of a plunge pool. And that concludes my outfall consideration discussion. And so again, in the outfall consideration, we're focused with velocity control. And there's in those guidance documents, there's a lot of interesting ways to achieve that velocity control. So as you're designing outfalls, not necessarily for project report, but in your future practices, bear in mind that the outfall itself is not just a pipe discharging into a stream, that there is some consideration on getting the water out of your system and then getting it slowed down when it gets into that stream. And it's mostly an art still. There's not a lot of proven techniques to do it. You have to make some educated guesses. Again, hydraulic modeling will be a principal tool to do that. And that concludes what I have for today. And so I want to wish everybody a happy Thanksgiving. If you're traveling, travel safely. Don't speed. I just read that the DPS, they're getting their Christmas bonuses based on the number of speeding tickets they write. So while they deserve a Christmas bonus, you don't need to be the one to give it to them. And if you're flying, wear 5 or 6 face masks and then wrap your head in a towel and hope for the best. Try not to do your best to avoid getting sick. I mean, that's kind of stupid advice because I don't know how to tell you to avoid getting sick. But try not to make your aunts and uncles, grandmas and grandpas, moms and dads sick at your family get-togethers. And I guess the best way to do that is just maintain an appropriate physical distance when you're around them. And if you're not traveling, well then have a happy Thanksgiving anyway. So with that, I'm going to end the session. I want to thank you for your attention and pretty much sticking to it on the night before the holiday begins, coming to class. So with that, have a great evening, everyone.